And now everybody at home is, why is he talking so weird? Where we ended was this question. This is going to be a long 75 minutes. Apparently it was filled with helium. I don't know. We ended with that last question dealing with mass in grams produced, 2 moles of CO2 are consumed. And what we were talking about is how we can use dimensional analysis or our unit factor method, however you want to look at it, to go through and solve and organize all those systems and move through it. Common comment from students, both at the college level and coming from high school, is that, well, I wasn't taught it this way when I was younger. What I was taught was involving some formula. And from that formula, I can go through and solve. And I need that formula so that I can solve. So I have to plug these things in. Okay? That method isn't necessarily wrong, but it then requires that you know the formula to do it. Okay? So if we look at 2 questions, how many moles are in 9.8 grams of calcium? How many grams are in 2.3 gram or moles of calcium? Those questions are intricately related, but if you go through and do a formula, you have to arrange the formula to allow you to go through and solve. Okay? So you would have to memorize those 2 pieces of information. You also then have to memorize what the heck is MM. Okay? And don't stress on that. But MM is molar mass. Okay? So you've now had to memorize 3 pieces of information. Okay? This isn't my method, by the way. That's why it's in air quotes or in normal quotes. Dimensional analysis just says, well, where do I find molar mass? Okay? Periodic table. I just need to know a process to how to solve and the molar mass. That process then applies to every single question out there. So I don't have to memorize formulas for how to go through and solve things. Okay? It does require that I know how and why I'm doing things. I have to think, heaven forbid, about what I'm doing. Okay? And yes, I fully understand that we as humans don't want to think. And I'm not blaming students for that. Because I do the same thing. We go through, we just multiply by 12. We divide by 3. Okay? That's how we get the answer. Okay? That works really well in select questions. And as long as you get the same question, you're golden. The instant the question changes, you're now dead in the water. Okay? And the biggest point that we're trying to get out of this kind of section is that I don't want you to memorize a formula to solve a chemistry question. Okay? And you're like, well, aren't you a chemistry teacher? Shouldn't you be teaching me to do that? How many of you are going to go on to be chemists? For those of you at home, that was nobody raising their hand. Okay? How many of you care what a mole is? Thank you. Maybe that's kind of interesting. Okay? Nobody cares what those unit systems are. Okay? So then why is somebody making you take this class? They're making you take this class because what somebody saw from the outside was that it provided you the opportunity to think about a new system and organize your thoughts in a logical fashion that prove you can solve complex problems. That's it. Right? It just so happens that those complex problems happen to be chemistry. Okay? That's pretty much the sole effort behind it. So to a certain extent, the content of chemistry is important to a select few people in the class that may need more advanced engineering or chemistry or biology classes. Okay? But for the most part, that's not the case. So what you need to get out of here is not just how to solve for moles or grams given moles, but how to solve, period. That's it. Okay? And so that's what we're attempting to talk about and move through. Okay? That said, maybe you want to make the decision that you don't want that. That is perfectly acceptable. I understand that desire. This is why there's the internet. You can go to the internet and you can look up formulas and you can memorize the crap out of the formulas and you can probably do very well on the exams. You are more than welcome to do that. Okay? Where you will probably struggle is where I ask you to show work or when I ask a question that doesn't fit into the tiny little boxes of your formulas. Right? That's okay. You'll probably still pass the class. Make sense? Okay. So why do I want this big, longer process? I want you to be able to problem solve. Okay? I know you aren't going to deal with chemistry in the future. That's okay. Okay? The other big reason is I want you to be able to think. That's it. Okay? I want you to be able to apply this knowledge out to as many different places as possible so that when you get hired for whatever position you're getting hired for, you have the ability to reason your way through it and you can find answers to complex problems. Because if all I've taught you to do is to use that one formula, when you go out into the world and say, oh my God, I got the perfect job that asked me to do this one formula, guess who else can do that one formula calculation? A computer. And a computer can do it 1 billion times faster than you. All somebody has to do is program a computer to do it. You've lost a job. Okay? So what I'm trying to teach you to do is to be the person creating the formulas so that you have a permanent job. You will always be needed because you know how to reason through that information. If I just give you the formulas, all I've given you is a piece of paper saying that you've passed the class. Okay? And that's not useful to me. Okay? In fact, I find that morally apprehensible. Okay? So with that, let's be exciting. We saw a question like this, right? Talking about all these conversions. So if every 1 mole of oxygen consumed, 2 moles of water produced, 9 grams of oxygen, 16 grams of oxygen, 1 blah, yeah, all those conversions. So lots and lots and lots of pieces of information went into this. Okay? And we saw that in exam 2. And you're like, well, jerk, you didn't tell me about moles. Okay, I didn't tell you about moles for a reason. I didn't want you thinking about moles. What I wanted you thinking about doing is what is the process to solve that question with all that given information. Have we talked about where to find a lot of that information? Yes. So what happens to the question? That 4 lines of text becomes this. You're responsible for the exact same calculation. Okay? So how do we do it? There was a bit of honesty in the back as I winced. Okay. Okay, what are we solving for? Yeah. I want grams of water. What am I starting with?
Grams of oxygen gas.
Grams of oxygen gas. What would that symbol be?
O2.
O2. Good. Okay. And now what I would argue we should do is we should look beginning to end and critically evaluate our unit to decide what are we going to need to do. Okay, our unit is composed of 2 pieces. What are those 2 pieces? Hydrogen and oxygen is not a piece of a unit. Hydrogen and oxygen would be a piece of water in this question. It's the substance and measurement are the words that we're using. Mass happens to be that measurement. Okay? So let's go through and look, beginning to end. Does the measurement unit change? No. Does the substance unit?
Yes.
Yes. So I do have to do a conversion. And as far as I'm concerned right now, all I have to do is one conversion, a substance conversion. Yeah? Where do I find information to convert substances? From a chemical formula. So I could go through and look at a chemical formula. Does that chemical formula of water have oxygen gas in it? Okay. Oh, interesting. The 2 people that shook their heads right next to each other did opposite head shakes. Fantastic. Okay, so we got a yes and a no. Who wants to volunteer?
Did I say no? It's not O2, it's just oxygen.
The oxygen in H2O is what? The oxygen atom. The oxygen from O2 is oxygen gas. It's a molecule. Those are 2 separate compounds. The symbols are similar because they're composed of the same type of element, but those are 2 separate things. So they aren't in the same thing. Okay? So does looking at the chemical formula allow me the conversion between hydrogen and or water and oxygen? Okay. Is there another place? So no, and then way to answer my next question. Is there another place to find it? Yes, in a chemical equation. Okay. There are a myriad of chemical equations, that could show the relationship between oxygen and water. I know it's not balanced, don't stress about that. That is a valid reaction. What reaction type? It's not a double replacement. I know it's 2 and 2. It's a combustion reaction. It's the reaction of an organic material with oxygen to produce CO2 and water. That's a combustion. You're responsible for acknowledging that that is a combustion reaction. Okay, unit 2. Should I be using that chemical equation? Let's assume it's balanced. Ta-da, magically balanced. I don't want to do it. Do I need to balance it?
Yes. Yeah.
Jerks. 2, what? And the 2 here? Oh, well, thank you. Cool. So there it is. It's balanced. It wasn't that bad. Should I be using this chemical formula to convert my substance? You're shaking your head no. Why?
Because we choosing H and O, we don't need carbon or carbon.
Maybe I understand where you're going from. You're saying, well, in this question we just care about oxygen and water. I don't care about carbon. Not quite. Why is that equation not valid to solve this question?
We're given a new, well, carbon, kind of what she's saying, but if we use it, it doesn't really get us anywhere. We're led up to a different thing that we can't change or solve.
Was it 2 and 2? 2 and 2. We'll address the issue with moles later. Okay. Would I be able to convert oxygen into water? I'm still seeing head shakes yet. No, so okay. We're just going to have to keep going with that. Grams of oxygen. Does that solve work? Yes. Is the answer I get when I run that in the calculator going to be valid?
No.
No. Oh, that was an awfully loud no. Why?
Because the question's asking specifies if there's excess hydrogen.
Where in my equation does it say anything about hydrogen? Oh, it doesn't. Because the equation I'm looking at that relates oxygen and water is not the question or the equation being asked about. We have to use the equation that's being asked about because that's the one that dictates the relationship between those substances. Okay? So what is the chemical equation that I'm being asked about?
H2 plus O2.
It says oxygen gas is reacted with hydrogen gas, then how many grams of water are produced? This is my new equation. If I left those 2's in there, is the equation balanced? No. The numbers I got from the balanced chemical equation that we previously looked at are going to give us the wrong conversion factor because we're looking at the wrong equation. Right? This is like me attempting to build a bicycle with car tires. The pieces don't align. I have to be using the pieces in the proper context. We have to use our chemical equation for forming water with hydrogen and oxygen. Is that chemical equation balanced?
No.
So how do we fix it? Dipstick, balance it. Yeah, how do we balance it? 2 waters, 2 hydrogens. Yeah? Okay? So that would allow me to convert the substance. Okay? I really didn't want to go as far as we did with the last one, okay, for this reason. Where should I place my substances? In this conversion, because that's what I want to do. I just want to convert my substances. Okay? Where should my substances go in that black line?
Grams of oxygen goes in the denominator.
Okay, so we'll announce that so the whole class can hear, and for the recording, I heard the grams of oxygen should go in the denominator. All we specified so far and all I asked about was the substance. I'm not asking about grams because that's going to be a very important distinction that we're going to have to make here in just a second. So again, I'm going to ask just the substance. Where should my substances show up in that black conversion? Why do I want the O2 to go in the denominator? So that I want it to cancel out. Okay? Can't cancel out yet because that's grams. And what's the problem with the O2 in the denominator? What have I not specified? A measurement yet. So I can't do a cancellation yet. Yeah?
Yeah.
What unit do I, or substance, sorry, do I want in the numerator? H2O. This conversion factor comes from what? From our balanced chemical equation. Phenomenal. What is the measurement unit from a balanced chemical equation? Moles. What numbers get associated with those? I'm a little unhappy with 2 over 1, but if we said 2 moles of water, 1 mole of oxygen, now I'd be okay with it. Okay? So what we've done is we called out the thing that we saw that we needed to convert. We needed to convert the substance. We did not force a unit system in there. Okay? And this is where I know you wanted to go with grams, because I wanted grams to cancel out. Does the balanced chemical equation tell you anything about mass? No, it is only a counting unit, so it has to be in moles. Which brings in a bit of a problem. We've now converted our substance, but at the same time, I did nothing to simplify my unit system. Grams of O2 cannot cancel moles of O2 because they are entirely different unit systems. Okay? So we've zeroed in on what we want to convert, but unfortunately we haven't simplified anything. That does kind of suck, so some people freak out at that. Okay? We'll address how those people would freak out and what they would do to fix here in a second. Okay? So we're not going to freak out because we know, hey, there's more stuff to do. Okay? In that more stuff, what needs to happen? Okay? I need the grams of oxygen to cancel, so where should I place the grams of oxygen? In the denominator. Do I know anything else about oxygen that I might want to get rid of? Moles of oxygen might be nice to get rid of, right? Do I know a conversion between the grams and moles for oxygen? Where's that conversion factor found? That is found on the periodic table. So I go to the periodic table. Oxygen is 16.00. There are 2 oxygens in O2. Excuse me. So I get a mass of 32. 32 goes where? With the grams of oxygen. 1 mole of oxygen. What happens to my units? Grams of oxygen cancel. Moles of oxygen cancel. That one step canceled a crap ton of units. That's phenomenal. Do I have my answer? No. I'm still short on my answer. I've got the substance. Do I have the measurement? Nope. So what has to happen?
Cancel out moles and 2 grams.
Moles of H2O needs to be canceled out, and ideally I get grams of H2O. Where do I find the relationship between the grams and moles? Periodic table, except now instead of looking at, for just oxygen, I will look at 2 hydrogens, 1 oxygen, and I get 18.02 grams of water is 1 mole of water. What happens to the units? The moles of water cancel. What answer would I now have? Grams of water. In the previous setup that we had, admittedly I forgot the last step. I apologize. But in that other one where we were using the combustion reaction, we could still convert grams of oxygen into grams of water, and we could have done that perfectly. It would still be the wrong answer because it wasn't referencing what the question asked about. So you have to use the context of the question to frame your conversions. Make sense? Okay. I'm going to do this one kind of small underneath. Grams, oxygen. grams of water. The standard protocol that you'll typically see people do when they go through to do this isn't in the sequence that we just showed. They switch it up and they do a different sequence. Okay? So people have gone to the tutoring center, right?
Mm-hmm.
Yeah? What do they tell you to do as step one after those two parts? You didn't ask the right questions at the tutoring center. Okay? They ask you a question?
We ask you the question, you give us the.
Well, no, don't talk to me. Talk to people in the tutoring center. Almost universally, they're going to tell you one thing. You should convert to moles. Grams of O2, moles of O2. And they would tell you where to find that? Periodic table. 1, 32 grams. Is that what we did? No. Why did they do that? So it cancels out grams of oxygen. Why'd you cancel out grams of oxygen? This is not what we needed. Cool, I can accept that. Does that conversion get me anything that I needed? No. Okay? So it's not wrong, but it's why are we making that step? Okay? The reason they're making that step is that the very first thing they're going to do is get into moles. Why are moles so powerful to get into? What can I do once I'm in moles? Convert substances. So what they have done is interchanged our blue for black. Why? Because they, doing a chess maneuver, realized that the next step is going to be converting substances. They've internalized that step. They've seen that pattern in enough of the questions they solved. That's it. Right? What I would argue is we don't need to solve as many questions as long as we're more deliberate about what we do for our conversions. Is the order in which we do those calculations going to matter? Mm-hmm. No. Okay? As long as they're all done. Make sense? Mm-hmm. We good with that? Okay. Should we try something different?
Yes.
Let's try something different. Okay? So what's going to happen in this next unit is we're going to add another thing. The thing that we're going to add is solubility. We're going to add water. Why might we add water?
It's everywhere.
It's everywhere. Water is the universal solvent. It found, close enough, everywhere. Right? So it's going to be our major kind of facilitator for all of our reactions. So if we think about water and solubility, what ends up happening is that water molecule is really, really good at dissolving things. Okay? And it's really good at dissolving things because of its basic structure. Okay? If I look at those bonds, okay, I'm just looking at those three elements. Let's just pick one bond to evaluate. What can you tell me is the difference between hydrogen and oxygen? There's a size difference, yeah. Mass is questionable to look at, okay, in most circumstances, and the reason the mass is going to be questionable is where is the mass found? For an element, physically, where is the mass found?
Nucleus.
In the nucleus. Where's the majority of the element, or what is the majority of the element? Everything else, the electrons. That mass is found in a marble in the superdome. The first thing I'm going to be concerned about is how to get into the superdome. Okay? So I have to get through that massive amount to find the marble. So the mass is a little bit less important, at least at our scale. Okay? Which means we're going to be looking at the electrons. Okay? Will do different elements attract electrons differently? Yes. And in fact, we even come up with a name for that property. Electronegativity. Oxygen is the second most electronegative element on the periodic table, meaning it really pulls on electrons, which means where did the electrons in that bond go? From hydrogen to the oxygen. Well, if oxygen starts to collect those electrons, what happens to it? It becomes negative. What happens to the hydrogen? It becomes positive. Is charge a good thing? Or let's say stable thing? No. Charge is highly reactive. Okay, so it is that charge that water is generating that's allowing it to do lots of strong interactions with its environment. The more charged it becomes, the more reactive it becomes. Okay? Is it formally negative? Like if I looked at sodium versus chlorine, I would show the same notation, right? The chlorine is more electronegative than the sodium. Right? Is the negative in chlorine the same as the negative in oxygen? Nice, cautious answer. That's good. No. Why? It's literally the bond that connects those atoms. In the sodium and chloride, what type of bond is that? That's an ionic bond. And the hydrogen and oxygen, that's our covalent bond. For those of you who want to call it hydrogen bonding, stop talking to biologists. They don't know what the F they're talking about. Okay? It's okay. Covalent bond versus ionic bond. And yet, the notation I'm representing those with looks identical, doesn't it? Okay, well, if they're different things, I'd better make sure that notation is different. How do I differentiate that? Is that oxygen actually becoming formally negative? Is it actually stealing the electrons from that bond? No, it's not. It's only partially stealing them. Okay? Because it is partially stealing them, I need a notation to differentiate it from the ionic bond. That notation needs to represent that it's a partial stealing. What do we use as a partial stealing?
Dotted line.
Dotted line's not a bad idea, except we're still talking about a chemical bond. I don't want to delete the bond. I know you see the dotted line there, it's something else. Okay. How would we denote that the temperature was changing? A little triangle, right? What symbol is that? A delta. That's because we have a large change in temperature. What if we had a tiny change in temperature? You just use a little tiny delta. What is delta? It's change. The symbol delta.
It's a triangle.
It's a triangle. Really? If I asked you for the symbol for B, what would you write? Those of you saying B, that's mean. Okay? If I asked you to write the symbol for B, what would you write? A line with two squiggles, okay? So I didn't write B?
That's what I'm saying.
Did I write B? Yeah? The line with two squiggles, what were you talking about? Are those both B? What is the difference between those? One's uppercase and one's lowercase. And you're like, why are you doing this? Ah, how do we do a lowercase triangle? There is a lowercase triangle. The old Navy triangle? I don't even know what that means. The triangle is coming from the Greek language. The D, or that triangle, is a capital delta, a capital D in the Greek language. Okay, because we're looking at a partial, not a full large distance, a small distance. We use the lowercase d, which is that weird squiggly looking thing. Okay, that is a lowercase delta. It is not an S. Here's an S. Here's a delta.
Is it connected on the bottom?
So it looks like I did what?
It looks like you sneeze while writing it.
That's what I thought you just said. Okay. For those of you going like, dude, your deltas suck, that's fine. We got a typewriter. Look at the typewriter. Look it up. It's called the delta notation. It's legit.
Oh, it's on the airlines. That's the sign that's on the airline, the Delta Airlines.
Oh, shit. Is it really?
I was just trying to figure out what you were drawing. I was like, is it the same sign on Delta Airlines?
I actually don't know that. I wonder if it is. That would be pretty cool. In any case, sorry. This is our delta notation. Focus. Our delta notation is just saying we have partial charges. Why is water so cool? It has very large partial charges.
It's like
Those-
derivatives, they use that delta too.
Yes, derivatives use the same thing. Okay? So it is a partial charge, partially negative, partially positive. And it is probably the largest partial charge we can get without becoming ionic. Right? Because of that, we get very large negatives and positives. Feel free to let me know about that when you get it. It is?
The capital one.
Yeah.
Oh, cool. There we go. those large partial charges now interact with other things that are charged, and that's why things dissolve in water. Okay? It is due to that huge polarity difference. That polarity difference is so huge that if I go through and look at that dotted line you see in there, we have that positive and negative aligning with each other. That interaction is now so strong that I invent a word for it to represent the strength of that interaction. Okay? The word that we picked was sequence of words that we picked was an unfortunate name, and we'll get to the detail of that unfortunate name in the next unit after exam 3. They call it hydrogen bonding, okay, or a hydrogen bond. It is not a bond. Yes, it involves hydrogen. Okay? It is the interaction between two separate molecules. But that interaction is so strong that water becomes an awesome solvent. Okay? That interaction is so strong that when I add something into it, it goes in and it breaks apart the interactions in that solid so that the solid can interact with water. Okay? That's what water is doing, is it's breaking all those things and making the solid dissolve. So when we take table salt, and if I was to say dissolve this, we've got our sodium ions and our chloride ions. Well, what would we see if this dissolved? Well, the sodium could interact with the chloride, or the sodium could interact with the oxygen, okay, in water. What color was I? And I can see this really strong interaction to the partial negative in oxygen. What makes it dissolve is that interaction, while strong, I can do a whole bunch of them. I can do them all the way around that sodium ion. That's why we dissolve it. It's the breaking of all of those forces. Okay? Just because it sounded like someone may have been mumbling it, you may hear reference to the solvent cage. Okay? That's exactly what's going on. It's the solvent molecules surrounding an individual solute to keep them dissolved.
Is it
Right.
actually like breaking up the sodium and the chloride?
In the case of ionic compounds that are soluble, yes, it is literally breaking the ionic bond between sodium and chlorine. This is why when we dissolve water, or dissolve salt, that is known as which process, chemical or physical? It's a chemical process because I've broken the bond. Okay? It's an ionic bond, so it's kind of a weak one, so it turns into this big, long debate, and it depends where you fall on that line.
Where does the chlorine go, though?
So the chlorine has what charge?
Negative.
A negative. So what might that negative chlorine be attracted to?
Okay. Sorry.
The positive hydrogens.
Okay.
Okay? So we get this big extended structure where those opposite charges just attract to each other. Okay? Those opposite charges are ultimately what drive all of our reactions. Okay? So it's pretty phenomenally cool. Okay? In this process, I'm breaking the connections between those. Have I broken the connections between molecules before? You're like, no, never done that before. Never put like a pot of water on the stove and turned on the heat and watched the water molecules that were all nice and close next to each other go flying away from each other. When I did say, I don't know, like a phase change. Yeah. Right? So solubility and phase changes are intricately tied to each other. And depending on which phase you're looking at or which transition, you'll see different things. So in this case, we'll look at sugar and salt. What phase are they? Solids. If I try to dissolve these in water, I'm trying to make them more liquid-like. What would I do to the temperature to make the solid more liquid-like? Increase it. So what happens when I increase temperature to the solubility? The salt's not an easy one to see, so don't look at the salt, look at the sugar. Okay? What happens to the solubility of sugar? How much of it dissolves when I increase the temperature? More. Okay? That tends to be a pretty standard result because as we increase temperature, we start to change phases to becoming more liquid-like. The same thing is happening when we try and dissolve things. We're making it more liquid-like. Okay? So now what we've got is a saturation curve. That line represents which of those words?
Saturated.
saturated. Yes, it represents sugar, the saturation curve for sugar. If we're on that line, that means the solution is saturated. Okay, what if I'm under that line? Okay, if I'm under that line, that means there's that little bit of distance that I could add more sugar to get it to dissolve. Which means that is unsaturated. What happens if I'm above that line? And actually, we're going to pick something else. We're going to go over to here. Okay, well now all of that is sugar that is dissolved more than a saturated solution. What was a saturated solution? What's a saturated solution? That is a solution that has the maximum amount of stuff dissolved in it. What's the purple dot? I have more than the maximum amount of things to dissolve in it. What? That doesn't make sense. How could that possibly be true? It's magic. Not quite. What we've done is created a supersaturated solution. We've tricked the solution into believing that it is allowed to dissolve, or really the solid into believing that it's allowed to dissolve. How did we trick it? We heat it up. Okay, we go up to say 60 degrees Celsius and we dissolve 300 grams and 100 milliliters of water. And then I slowly cool it down. As I cool down, what happens? All I'm doing is changing the temperature. If I cool it just right, I've now tricked the solution, the solid, to stay in solution. Okay? So I've tricked someone to walk into a dark house. Okay? What do I do once they've It's more playful than that. What would I now do when I've tricked my wife to walk into the dark house?
Scare her.
I could jump out and scare her, and what happens? I usually get beat up. But what happens if I jump out and now scare the solution? It realizes, oh crap, I should not be in solution, and what do the solids do? They precipitate out. Okay? In a sometimes neat fashion. You've seen those little sticks with like rock candy, like sugar crystallized on them? That you're taking advantage of that. That's exactly what's happening. Okay, you guys did a lab, the heat and energy lab, the sodium acetate trihydrate. Yep. Did you guys actually do it?
Yeah.
Yeah. Did it work?
Not for everyone.
Yeah, that's kind of what happens. Okay. There's a video you could watch. Look up hot ice idiot.
I've seen that.
Feel free to look. Yeah, it's stupid. Okay. Okay. But that shows that process. It's the same thing. Okay. We've tricked the solution into staying a solution, or the solid into staying a solution. Okay. When we suddenly let it know what happens, it'll precipitate back out. Okay. So we can get supersaturated solutions. Okay. So that's how we interpret that graph. That's all I really want out of it. Yes, and then yes.
But how do you get tricked? Like, what's the process behind that?
Well, how would I let my wife know that I've scared her?
Well,
I could jump out and shake her. Guess what you do to the solution?
no.
You jump out and shake it.
If it's
And you're like, that's all you do? Yes! That's literally it.
I know, but if it's dissolved in it, does that mean there's space for it? If there's not space for it, then
So what's happened is you've tricked it into aligning in such a way that there is just enough space in that steady state. This is why when you jump out and shake it, you've broken that steady state, and that's when it realizes, oh, whoops, we shouldn't all be dissolved in here. Let's get out of there. Okay? And that's, at a very personified way, that's what's happening.
Kind of like what I was going to ask how the heat allows it to dissolve all this kind of structure.
So what the heat does is it causes everything to move more.
Yeah.
The more it moves, it weakens all those interactions so that we can get it to dissolve at that higher state. Okay, that's how we get the saturated level.
Okay, so that has nothing to do with the amount of materials.
Not as much. They're related to each other off of that curve. Yeah. Okay. And unfortunately, I'm going to cut it there because while it's kind of neat, I don't want to spend too much more time on it. Okay. We can do this for virtually every substance. What do you notice about most of those substances?
they go up at the temperature.
They all go up. As you increase the temperature, what happens? Their solubilities all go up. Is that always true? No. There are some cases where they don't. Okay? Those are cases that people tend to study, because why would it do that? That doesn't make physical sense. Okay? So those tend to be the ones that are more studied, and you can get some interesting, bizarre things happening in those. Okay? So, we now have solutions. I can dissolve sugar in water, so I get a thing. Okay, so now let's go back to our reactions. So that was all we get on not doing numbers. Now we get more numbers. So I've got this reaction. What type of reaction is that? That is a double replacement reaction. Just because I heard the usage somewhere else, that actually makes sense. Instead of saying double replacement, we could say double displacement, which is actually a better word for it because the ions are displacing each other in those locations. Same thing for single replacement. We could call it a single displacement. I've also heard people use metathesis. The reason I don't use that is I can't say it. That's pretty much the only reason. And it's not metastasize. It's, metathesis, I don't know, whatever. You'll sometimes hear people refer to double replacements like that. Okay? So, how do we quantify the amount of the silver bromide produced?
Coefficient?
No, we're in the lab. I want to quantify it. I ran the experiment. Ta-da! How do I say this is how much I produced?
Mass of it.
Why you say mass?
Because it's a solid.
We look at our chemical equation and it says it's an effing solid. So what do? We weigh it. That's really straightforward and simple. I like that. That's cool. Okay, where did it come from? Where did the silver bromide come from? How did I get it? It came from 2 aqueous solutions. I mixed aluminum bromide with silver nitrate. Okay, 2 aqueous solutions. How did I measure them? Why would I measure them with volume and not mass? They're physical state. They're liquids. It's easier to measure liquids by volume. So cool. Ignore that. If I was to go through and say, I started with 5 milliliters of silver nitrate, and I wanted to say, know the grams of silver bromide produced. Okay? Silver bromide should be in units of grams. My silver nitrate, because it's a solution, you guys did a fantastic job, aqueous, is milliliters. What would I need to do this conversion? Okay, it is going to be a unit conversion. What unit conversions am I going to need?
Moles to grams. Grams to moles.
Okay, we've got moles to grams. Is that a standard one? Okay, I'll accept that.
Liters to moles.
Liters to moles?
4 milliliters.
Where did that come from? And don't tell me, you just showed me, that doesn't count. Why do we need this milliliters to moles thing?
Go anywhere.
Couldn't I do milliliters to grams? Milliliters to moles is not going to be a change in substance because that's changing the measurement. Okay, so I will say for sure we will need a moles to moles. Okay, but what I'm asking is in here.
Milliliters to grams isn't really a thing.
What is grams a measure of? Mass. What is milliliters a measure of? There's not really a thing that relates mass and volume.
Density.
Damn it, density. You're not too far off. Okay? So your suggestion, because you did an awesome job reading, presumably, you were like milliliters to moles. Why not use density?
You're adding it.
You have to weigh the aqueous solutions do.
No, because I could look up the density. The density applies to what? For what?
Silver nitrate.
For a single substance. What is the silver nitrate? Is that a single substance? Why are you saying no? What's that? It's silver and nitrate, but together that makes a single substance. That's a molecule. Why is the silver nitrate not a single substance? Because you are absolutely 100% correct. It is not a single substance, and that's what brings in the next unit system.
Silver has a different.
Nope.
It dissolved in water.
Is the silver nitrate a single substance? The phase is aqueous. If I go through to measure the density of the silver nitrate, am I looking up the density of silver nitrate? No, because it's not just silver nitrate. It's an aqueous solution. It's silver nitrate and water. Even if I get the density of that solution, how much of that mass is silver nitrate? I need another conversion to come up with that. I would need to know how much of that substance is dissolved in that water. Okay? What word might we use for this? And before you start saying molarity, no. Concentration, thank you. We're looking at a concentration. Is concentration something that you've seen before?
No.
Okay. Really? Anybody had orange juice? Yeah. Have you had orange? Shh. Have you had orange juice? Yeah. What does it say on the bottle? From concentrate.
No.
Have we dealt with concentration? Yes. Everybody's dealt with concentration. And I picked orange juice because that was a more age-appropriate example. Okay. We've got other less age-appropriate examples.
Yeah, like IV fluids.
Fair enough. Yeah, IV fluids. That's a good one. Let's stick with that. The concentration of IV fluids. The salt present in those fluids. Okay? When you inject someone with an IV, they've got that bag full of solution in it. If that was pure salt, that's going to F you up pretty badly.
Yeah.
Okay? So the concentration is important. Okay? And we have to monitor that and evaluate that carefully. If we go out into the world and think about all the concentrations of things we see, we typically see them in what units? Percent by? Volume is the most common one. ABV. Well, I'm going to do the path. ABV. What's ABV? Alcohol by volume. That's why it's called ABV. So when you look at your next can of alcohol, bottle of alcohol, however you want to look at it, and it says 4% ABV, it's alcohol by volume. They measured the amount of alcohol in the volume of the total substance. That's how they got that percent. Okay? So in that case, they're measuring milliliters to milliliters. On an IV solution, I haven't looked at them, but I'm going to guess at their units. You clearly knew more than I did, because you suggested IV fluids. Has anybody looked at the concentration for those?
0.9%. It's 0.9% sodium chloride is what it says.
What the hell? 0.9% by what?
Per milliliter, I think. Sodium chloride per milliliter is what it says.
Okay, so it's probably 0.9 grams per, that's really high, per milliliter of water? It's got to be per liter of water. Or 100 milliliters of water. I don't know, but there's a measurement there. A mass over kind of the volume. Why would we do the mass of sodium chloride over the volume of the water? Why not just mass and mass? What is the phase for sodium chloride?
Solid.
A solid. What is the phase for water?
Liquid.
Liquid. That's why they're changing the unit systems, because they're going based off the standard. So when you hear mass by volume, you're doing milliliters to milliliters. Mass or percent by mass, it's typically mass to mass. If it's a solution, it's probably mass, and we're using water, in which case it's still a by mass, but water's density is 1, so it's a 1-to-1 ratio. Okay? So we could use mass. Chemists decided for concentration we weren't going to use mass. Why might we have decided not to use mass? What does a chemist do? Invent new things from chemicals. Okay? So they're doing chemical reactions. What unit do you need in a chemical reaction? Moles. Our chemical reactions show moles. So why do we not use mass by volume? Because we know we're going to convert them into something else anyway, and that converting into something else needs to happen in moles. So when I go through and represent all of my solutions in chemistry, I decide to pick moles by volume. Okay? So this is moles of a substance per liter of the total solution. Okay? All this is a new conversion factor, just like density. Okay? And just like density, we don't just memorize. I'm kind of telling you to memorize this, sort of. Density, we come up with a new name. We don't just say, well, it's this thing, whatever this thing is, I don't know what it is, but it's mass over volume. We invented a term to represent mass over volume, which was density. Here we're doing the exact same thing. We're inventing a term to represent the moles of a substance over the liters of a solution. That term is molarity. The symbol we give to it, capital M. Not lowercase, because that's meters. Okay? We get tons of M's, it becomes a problem. Okay? So we've got capital M. So when you look at a question, almost always they'll give you a capital M. They'll say 3 molar. Think back to the labs. Okay? For those of you in lab right after this, you're doing the single replacement lab. Look at the reagent bottles, okay? And they'll say silver nitrate. But in front of it, it'll say 0.01 capital M silver nitrate. What are they including on the bottle? The molarity. They're telling you the concentration of the solution. If you think back to all of your experiments, those concentrations have been on every single one of your bottles because the concentration makes the poison. Okay? Have you heard that apple seeds have cyanide in them?
Yeah.
How many of you have eaten an apple seed? They do. You hadn't heard that? Okay, why are you still here? Isn't cyanide like poison?
And higher dose concentrations.
The concentration makes the poison. If you eat enough apple seeds, yes, you can expose yourself to enough cyanide and you can potentially cause problems. Okay? So it's all about that concentration. That's why when we look at our reagents and our solutions in lab, we have to specify the concentration. Because one concentration could be insanely toxic, another concentration could be meaningless. Okay? So the concentrations will always get put there. Okay? But because we now have a new unit, guess what we get to do?
Use it.
We get to do some conversions. Okay? Do you want to walk through on this one? Mm-hmm. Yeah? Okay. What is the molarity of a solution containing 24.0 grams of sodium hydroxide in a 0.1 liters of solution? Okay? Just like with every other question, the process is the same. What are we solving for? Molarity. Okay? And I'm going to argue the molarity of a solution, even better. Right? And we'll adjust solution here in a second. Okay? We should stop using the word molarity. It's fine to write it. It simplifies what we write out. But as soon as you see the word molarity, you should not be saying, oh, I'm solving for molarity. Okay? Because molarity shows up in one place. In the word molarity. So that's a dumb thing to do. It is the moles per liter. The moles of what in this case? What is the substance being dissolved in this solution?
Sodium hydroxide.
This is the moles of sodium hydroxide per liter of solution. Does anybody want to write out solution every single time? Okay, good. I write SLN. SOLN. Those letters. Okay? What are we given to start with? Grams of, this is unfortunate, it's called a widow because we're breaking the information off. If on a test question you saw it break like this, what you should probably do is write that extra information there. Grams of sodium hydroxide and? Are you given either the moles of sodium hydroxide or the liters of solution? You're given the liters of solution. Sweet. So we can insert this immediately into our solve. Where do I want the liters of solution to show up? On the bottom. What is the number associated with that? 0.100. What number shows up in the numerator?
Grams of NaOH.
Not grams of NaOH. Grams of NaOH is a separate piece of information. I don't want to combine things. That is my personal choice. You don't want to do that, that's okay. But I would argue you should not combine things. 1. Okay, so cool. This sets it up where I get liters of solution, exactly where I want them to be. What do I want in the numerator? Moles of sodium hydroxide. Have I done that yet? No. So I want moles of sodium hydroxide in the numerator. Am I given that? No. So I give up and go home? No. It's not time yet. So now I have a choice. It is my choice to now look at the given information and say, could I somehow relate the given information to moles so that I can come up with a conversion factor here? Or do I just want to say, well, sodium hydroxide is the substance. It's showing up in the numerator. So instead of writing moles of sodium hydroxide, I'm going to write grams of sodium hydroxide. Everybody understand those two choices? Okay, I saw one head shake no, that is fine. Okay. We have 2 routes to go. If we run the top route, we don't know a number to place. In the bottom route, what do we place in the denominator? 1. That is our given piece of information. That's all we can put there. Okay, so let's hold off on the bottom route. Okay, let's take a look at the top. What do we want to convert moles of sodium hydroxide to? Why do you want to convert them to grams of sodium hydroxide?
You still have to like get rid of the grams eventually, but that's like
Okay. So what you're propagating out in your head, which is fantastic, good job. He's propagating out that if I had mole to gram here, if I had that conversion, I don't know if it exists, but if I had that, I could then do grams of sodium hydroxide here, and those units would cancel. Am I getting you right? Cool. Okay. Bottom case. Is grams of sodium hydroxide what we want for an answer? No. So what's our next step? Whoa. What's our next step? I want grams of sodium hydroxide to cancel. Okay. What do I want in the numerator? Okay. Do you know the 24.0 grams of sodium hydroxide? Was that given information? Yes. Can you come up with a conversion between grams and moles? Where's the conversion between grams and moles found? The periodic table. So we go to the periodic table and we do, because I don't feel like doing harder math, 23 plus 17, 40. Yeah? That was pretty cool. Can't believe I just did that. 40 grams is 1 mole. 40 grams is 1 mole. Oh, the top calculation, we forgot a step. Are we given just the grams of sodium hydroxide? Oh yeah, that was given in the question. So what could I do? 24.0 over 1. Do both of these calculations end at the same result?
Yeah.
Yes. Do these look so drastically different that you're like, oh my God, I can't understand why one of these would work? That's amazing. Usually I get people, I have no idea how you did that. And then I show the other one, and they're like, I still don't know how you did that. So you guys are looking at both of those, and you're like, I understand how someone could do either of those. Legit. Okay.
cool with that.
Okay. Not that I don't believe you. Do that one on your own. Where's your tool writing? We'll just go through and I'll talk through it while you're writing, but I'll use your work. So if we go through, Couple approaches on this. When I walked around and helped someone, we went through and did a slightly different method than what's being shown here. Okay, so let's go through and stepwise this. So the work that was suggested by one of your colleagues, of course, I'm not doing that right, because undoubtedly they followed the method, but based on their work, I'm kind of nervous they didn't follow the method.
Maybe not.
And they wrote grams of our potassium dichromate on the far right, because that's what we were solving for. Okay, they went through and then you started left to right, right?
Mm-hmm.
Yeah. Okay. They went through and then did 0.15 moles over liters. Okay? And then they actually started doing some calculations. So right out of the gate, I want to address that. Okay? Why? What's the substance? Why did you place the moles over liters like that? Because couldn't I have just written liters? Still starting with the same thing, but I'm placing it in a different location. So why is red better than blue?
Because molarity is moles over liter, and that's what you're trying to get.
We're not trying to get molarity, we're trying to get grams. We are given molarity, but just because we're given it doesn't mean that number shows up in the numerator. It could just as easily have shown up in the denominator. So again, the question becomes, why are we placing the moles in the numerator and not the denominator?
Because the next step you have to cancel it.
Well, regardless, even in the blue one, the next step I'm going to have to cancel stuff.
What's the moles for H2CR2?
Okay? So my biggest call out on this is going to be, you didn't write complete units. What are the complete units? K2CR2O7 over liters of solution. With that subtle bit of information, it doesn't make sense to say the red one is better than the blue one. Why?
Because the substance makes more sense being on the in the numerator.
When we look at our answer, where does our substance show up?
At the end.
Yes, at the end in the answer, but where? In the numerator. So where should my substance show up in my work? In the numerator. Okay? Use those keys to help kind of lock you into those locations. If you're doing it intuitively correct, that's fine. Okay? What I'm trying to do is provide that extra edge so that you don't have to rely on your intuition. Okay? And for those of you that don't have that intuition, I'm trying to set you up so now you don't need to worry about an intuition. Make sense? Okay. The subtle change that I made when working with somebody else was I actually immediately had them go through and write out the given information. The information was 0.15 moles of K2CR2O7 per 1 liter of solution. This removes this stupid capital M that's confusing and now puts it into a format that I can potentially work with. I also had them write down that that's 125.0 milliliters of solution. I can now see those more complex units and can potentially manipulate this. Okay? At this time, the question that I would ask is, do we want moles of potassium dichromate in our answer? No. Do we want liters of solution? Do we want liters of solution in the answer? No. Okay? So we have two things that we have to fix. It is up to you to decide what you want to fix. In the case of our volunteered example, they decided to go through and fix the liters of solution. So they wrote liters of solution presumably in the numerator. Again, they left off the substance. You should be fixing that stuff. Okay? Are we given the liters of the solution?
Yes.
Liters of the solution? No. What we are given is milliliters. And so you made the awesome call out that milliliters of solution, okay, can be related to the liters of solution. Okay, which I believe is the conversion you were fishing for earlier, but you missed the liters of solution, which is why you had a problem finding it. Okay? So now we'd have to know that conversion factor. There are a variety of ways to memorize that. I told you memorize the power of 10, goes with the core unit, and that's our setup. If you memorize something else, that's cool. It's still valid what you wrote.
Okay.
Okay? This fix the liters of solution. I'll see your hand in a second. Milliliters of solution needs to cancel. Are we given the milliliters of solution? Yes, what was it? 125.0. What goes in the denominator? Fantastic. 1. Hand?
Will we get marked off if we don't do that second step? We just convert it in our head and then write it down? Like
I understand what you're asking. Yeah, I know what you're saying. So the question for those at home is in this: would you lose points if you said, "Did I do it right?" Yeah. Yeah.
Sure.
That liters of solution.
Mm-hmm.
In a show your work, yes.
Okay. 'Cause
You
I
need to
feel
show
like
that.
They got marked off the last one, and the answer was right.
Because that's kind of
Yeah.
what I did with like.
And so you can see that. I don't want you skipping right now in the show your work. In more advanced classes, they probably won't care for that. I want to see that work in a show your work. Okay. In a straight multiple choice, I don't need to see the work. I still recommend you do it because it is very easy to screw that up and shift the decimal the wrong place. All right. So that's why I tell you I want to see the work now. Okay. Okay. Would this then be the answer?
No.
No, because we would end with, we would just have moles of potassium dichromate. Do we want that?
No.
No, so what do we have to do?
Grams.
Moles, oh my gosh. Sometimes our solves just keep on going. Our solve, keep on. Moles of potassium dichromate needs to cancel. What do I need?
Grams.
Grams of potassium dichromate. Where'd it go? Where do I find that conversion? Periodic, the table. Can I get a shout out on a number?
294.2.
Do I get a confirmation?
Yeah.
Okay, so it sounds like that one's correct. Okay, now I can go through and enter it all into the calculator, punch it in, get a number. Yay! 5.16?
Or 5.516, right?
5.516. Because you gave me a number, we'll talk through it. 5.516. What do we say, grams? How many sig figs?
2.
Not 2. In your work that you wrote down, because I saw it, yes, 2 would be correct. However, what did you do? You forgot the 0 on the 0.150. There's 3 sig figs there. 3 sig figs comes in as our answer.
5.51 by 2.
Because that's larger, I need to add 1. I get 5.52 grams potassium, all that fun stuff. Thank you for paying attention and staying a little bit late. You are done. If you're really curious, there's a fun question.